We're picking up where we left off, talking about a geometric sequence in our last section, and now we're talking about a geometric series. We'll also be talking about a geometric sum. So let's look at the difference between a geometric sum and a geometric series. Now we know the general idea of what a geometric sequence was. And if you remember, it looks like something k equals 0, and this k could be a j or some other variable as well. K equals 0 to some n minus 1, and then we had a times r to the n, or a times r to the k if we're going to use k as our indice. So this is a geometric sum. A geometric series goes k equals 0 to infinity, and again it has the same general shape, a times r to the k. Now when we're talking about these, and I'm talking about a geometric sum, when I actually find the values of these, and we'll look at some specific examples, I get a finite sum here. I get a number. It could be a fraction, it could be a decimal, it could be an integer as well. But I get a finite sum when I'm working with the geometric sum, hence the name sum. When we're working with the geometric series, I don't know what I'm going to get. I could do something like converge, or it could diverge. And it all depends on the value of r, and r is called the ratio. So let's go ahead and look at the parts of the geometric series or the geometric sum once again. A is this constant for every single term, and r, this value of r, is the common ratio. It's what I'm multiplying each value by. So r, for both of these, is the ratio. So when we're starting to move toward whether we converge or diverge, we have a set of rules that we look at. So for a geometric series, the geometric series will converge if the absolute value of r, this ratio, is less than 1. And it will converge to a over 1 minus r. Now it will diverge for any other case. So it will diverge otherwise. Now the interesting thing to think about here is, so if we say the absolute value of r is less than 1, we're basically saying it's a proper fraction, like 1/2, 2/3. And so if we take something like a half to a power, it gets smaller, 1/2, 1/4, 1/8, 1/16. Now if we had a number, let's say r was 2, and we take that to a power, it would go 2, 4, 8, 16, 32, and we could see that it would diverge. So that's why we're saying it diverges otherwise, and it converges basically if it's a proper fraction, positive or negative. Now for our finite sum, this is a little bit different over here. For our finite sum, if we think about k equals 0 to n minus 1, how many things am I adding up here? So if we go, let's say k equals 0 to 4, a times r to the k, I am looking at 0, 1, 2, 3, 4. So I'm looking at plugging in 0, seeing what I get, plugging in 1, 2, 3, and 4. So what we get here is n is equal to 5. So n, the number of terms that I have here, is always one more than my upper indice right here. So n equals 5 in this particular case. Now what we have then is a partial sum. So for this partial sum, or this finite sum that I'm looking for, this would sum to a 1 minus r to the n. I'm going to make my parentheses a little bit bigger here. A times the quantity 1 minus r to the n all over 1 minus r. So these are kind of some of the things that we want to keep track of while we're working through this particular section. We'll work a lot of problems just so you kind of get familiar with them. Keep in mind, some of these we're going to get into some pretty big numbers, and so we'll definitely be using a calculator, but don't shortcut anything at all. Make sure you're showing all of your work. Make sure that you're finding your common denominators and everything. What you don't want to do is just plug them into your calculator and then pop out a solution with no work, because there'll be no credit involved. So first of all, let's go ahead and get started. And let's look at a problem where we're evaluating a geometric sum. So remember, a geometric sum, I don't have to check whether it converges or diverges. It goes to a finite value. And the geometric sum that we want to look at is k equal 2 to 11. Now most geometric series, if you come up here, a geometric sum starts at 0. So I have to compensate for the fact that I'm no longer starting at 0. but we'll look at how we're going to do that. And this is just 3 to the k. Now I want to look at a couple different things. First of all, this is starting at 2 and going to 11. Now we're used to a times r to the n, so I'm going to put the a in here as a 1. And I'm used to n up here, but I have to remind myself to use k. I'm going to put the 1 in here so we understand what a is. R is definitely 3. So if this was an infinite series, this would diverge because the absolute value of 3 would be greater than 1. But this is a finite sum. It's only going from k equal 2 to 11. So what I need to do is I need to rewrite this. I need to rewrite this as k equals 0 to 11, 1 times 3 to the k. Now let's think about what's going on here. If we go k equals 0 to 11, that's going to be too high. That's going to be too large. I need to subtract off the case where k equals 0 to 1. And then I'll be left with k equal 2 to 11. So the way that you could think about this is I want to figure out what the sum is from 2 to 11. So I want to know what this is. This is what I'm interested in. So what I do then is I find 0 to 11, and then I subtract off this piece right here. So that's what I'm looking at when I'm trying to find these particular values. Now you might say, well, wait a minute, this goes up to 2, so you should be going 0 to 2 here. But remember, this is an integer. These are integers. So I want to plug in the 0 and the 1. The 2 starts out with our next one. So I just want the 0 and 1 cut off. So that's kind of what we're looking at there. So this is still 1 times 3 to the k. So k equals 0 to 11. If we think about the number of terms that this is, 0 to 11 would be n equal 12 terms. 0 to 1 would be 0 and 1. It would be 2 terms. So we're going to use the finite sum formula here. In the finite sum formula, it looks like a times 1 minus r to the nth power over 1 minus r. So for our example, a is definitely 1. 1 minus r, which is 3 to the n, 3 to the 12th for my first one, all over 1 minus 3. Okay, so that's for my 0 to 11. And it's 12 terms because we count the 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 would be 12 terms. And then we go ahead and subtract off a, 1 minus 3 to the second, because in our second one right here we have 2 terms, 0 and 1, all over 1 minus 3. So this is basically what I'm working with to find the sum. Now I could have done this another way, and I'll show you that too, but it's a lot more computationally difficult. So as we're plugging in here, again, these values, they're going to be really, really large. So as I look at 3 to the 12th, and I wouldn't expect that you would multiply that out. If we have these on an exam, they'd be reasonable numbers, and if they're on handwritten homework, of course, you could use your calculator. So we get 531,441. But we don't skip any steps. 1 minus 3 is a negative 2. So that's my first term. Let's go ahead and subtract off my second now. I still get that negative 2 in the denominator. And the numerator is going to be 1 minus 3 squared. And of course 3 squared, that's easy enough to work with. That's 1 minus 9. And we just need to really simplify the heck out of this thing. So as we're working through this, we end up with 1 minus 531,441. That's going to give me a negative 531,440 over a negative 2. Minus 1 minus 9 is a negative 8 over a negative 2. Now I have this negative 2 that's my common denominator, so I really can keep it as is, or I can reduce these fractions because it looks like everything's even here. So just to start off with, I have a negative divided by negative, which will be a positive. 531,440 divided by 2 would be 265,720. Okay, so negative divided by negative is that positive. And then over here, a negative divided by a negative is a positive, but I also have that negative out front. 8 divided by 2 is 4. And for this one, I'm left with 265,716. So that's my finite sum. And that's actually a lot easier than going the long way. So the long way would look something, again, let's go ahead and copy down our original problem. We have k equal 2 to 11 of 3 to the k. And again, 1 times 3 to the k. So what this means is 3 squared plus 3 cubed plus 3 to the 4th plus 3 to the 5th plus 3 to the 6th, all the way up to 3 to the 11th. So that would be the other alternative of trying to figure out what this finite sum is, this geometric sum is. And I think using our shortcut formulas here for the finite sum formula works a lot better than actually taking these and saying, okay, that'd be 9 plus 27 plus 81. You can see the numbers are going to get really big really fast. So definitely want to be using these formulas. Now sometimes the geometric series or sum is not given to you. This function that produces that sum isn't given to you, but you're given a raw sequence and then asked to kind of work from there. So let's look at an example where that's the case. These are kind of fun to do. So we are going to be given a geometric sum, and what we want to do is we want to find the actual sum. So we have something like, let's say, like 1/2 plus 1/6 plus 1/18 plus 1/54, and this same pattern will continue until we get up to 1 over 1458. So what we're looking at here is we're trying to come up with, how could I rewrite this into some sort of a geometric series or geometric sum. So I want it to go k equals 0 to something. I have to figure that out. And then I have an a times some r to the k. So we need to fill in these missing values. Now before I do that, I want to try and look at this and see if there's anything going on that I can figure out. So when I look at the 1/2 to a 6, it looks like the numerator is always a 1. But let's look at the denominator. When we get from 2 to 6, I could add 4. But 6 plus 4 would be 10, not 18. So let's think about how else we could do this. What about 2 times 3 is 6? 6 times 3 is 18. 18 times 3 is 54. So it looks like to me that common ratio that we're looking at has something to do with a 1/3. So let's go ahead and write these out a little bit. This would be a 1/2 times 1/3 to the 0. Remember, anything to the 0 power is 1. 1 times a 1/2 is a 1/2. Next one would be 1/2 times 1/3 to the 1st. The next one would be 1/2 times 1/3 times 1/3 would be 1/3 quantity squared. 1/2 times 1/3 cubed. Now the question is, what is this last one? 1/3 to the what? Well, in order to figure out what this power is, we'd take 1458 and we divide it by 2. And then we take that and we look at the root. So 1458 divided by 2. 2 goes into 14 7 times. 2 goes into 5 twice. So this would be 729. So basically what I want to know here then is 3 to what power is equal to 729? Well, 729 is a familiar number if you think about powers of 3 a lot, I guess. And so this one's not too tough to figure out at all. So solving for here, if you didn't know this one directly, you could take the natural log of both sides and solve. But basically we get 3 to the 6th is 729. And again, if you want to think about breaking that down into parts that are familiar, this is 3 squared, 3 squared, 3 squared. So I have 9 times 9 times 9. 81 times 9 is 729. So that breaks down pretty slick. And again, it's not too bad to do in your head. So that's to the 6th power. So if we try and write out our series, we can see that the common value here of a 1/2 I can pull out front. So that's my value for A. Now R is this common ratio of a 1/3. Now it does look like I start at 0 and it does look like I go to 6. So there's my series that I'm looking at. Now if I want to find the sum of this, What I need to know is what is n, how many terms there are. So terms would be, counting here, I'd have 1 would be, this would be my first term, 1, 2, 3, 4, and then I'd have 5, 6, and this would be my 7th term here. So n is equal to 7 in this particular case. There's 7 terms. So if I was interested in the sum would be a times 1 minus r to the n over 1 minus r. A is equal to 1/2. 1 minus r to the n, that would be 1 minus the quantity 1/3 to the 7th, all over 1 minus 1/3. And again, our numbers will get pretty big here. On the handwritten homework, you have to show all these steps. You don't want to skip any steps at all. You don't want to, make me wonder what happened. How did you get from point A to point B? Always make sure that that's in there. On the exam, our numbers are not going to be so large. We should be able to do those by hand or in your head. Now in the denominator over here, I have 1 minus 1/3. 3/3 minus 1/3 is 2/3. And then over here, I have 1 minus 3 to the 7th. Well, we already know what 3 to the 6 is over here, so let's just multiply this by one more 3. 9 times 3 is 27. So it looks like it's 2187. Okay, and then we're just going to simplify from here. I have the half out front. When you divide by 2/3, it's the same as multiplying by 3/2, so I can pop that up front. And then I have this 2187 minus 1 over 2187. That's finding that common denominator over here. So it looks like I have 3/4. 2187 minus 1 is 2186 over 2187. Now this will reduce, so let's go ahead and think about trying to reduce this. So for 2186 does not go into 4 does not go into 2186, but they're both divisible by 2. So 2 goes into 4 twice. 2 goes into 2186. Let's see, 1, 0, 9 times 2, 1093. And 3 does go into 2187. 3 goes into 21 7 times. 3 times 2 is 6. 729. So it looks like I'm left with 1093 over 2 times 729. Continuing to simplify that, we get 1093 over 1400. 29 plus 29 is 58. So that would be my exact answer. So if they're asking for a fraction, this would be your solution. That would be the sum. If they're wanting you to round this, then you would go ahead and divide that out and then round it, as they say, to however many decimal places. So you have to be really careful about how you read your solutions and also read the directions to see how they want the solution submitted. I think these are the most fun ones because you get to come up with this nice series as well up here. And then you also get to find out what the geometric sum is of that geometric sum up top. Now let's go ahead and look at a few geometric series. These we'll go ahead and take from 0 to infinity for our indice. And what we want to do is we want to determine if they converge or diverge. And if they converge, we want to know what do they converge to. So let's go ahead and look at a few examples. Let's look at k equals 0 to infinity of 2/7 to the k. Now again, I always like to put in my value for a here. So I always put in the 1 times 2/7, and that's the 2 and the 7, 2/7 quantity to the k. So if I want to figure out if this converges or diverges, this is the work I need to show. I need to show what r is. R is 2/7, and then I need to look at the absolute value of 2/7, and I need to say, okay, is it less than 1 or is it otherwise? Is it greater than 1? Well, this is definitely less than 1, so therefore it will converge. Now remember, that rule came from up here at the beginning. If the absolute value of r, if the absolute value of the ratio is less than 1, it will converge, and it diverges otherwise for any other case. So we know it converges, but let's go ahead and talk about what it converges to. It converges to a over 1 minus r. A in this case is 1. 1 minus 2/7. 7 sevenths minus 2 sevenths is 5 sevenths. When you divide by a fraction, you multiply by the reciprocal, so this would pop up top, and then it would converge to the value of 7 fifths. Now this works because this goes from 0 to infinity. I don't have to worry about subtracting off a piece. It starts at 0 and it goes clear out to infinity. Let's look at another example. Let's look at k equals 0 to infinity. And this time let's go ahead and look at, let's have something with a negative in it. So let's do negative 0.7 to the k. And again, I like to rewrite mine, so I have that value of a in there. So I have a times r, negative 0.7 to the k. So the first thing I need to do is I need to identify r. R in this case is negative 0.7. And then I need to take the absolute value and then compare that to 1. So the absolute value of negative 0.7 is 0.7, which is clearly less than 1. So therefore this converges. And it converges to a over 1 minus r. So a in this case is 1. We can pull that from right here. And then 1 minus, now this is the tricky part, r is a negative 0.7, so I need to make sure I have the subtraction and the minus sign. So I need the subtraction sign and the fact that r is negative. So rewriting, I have 1 over 1 plus 0.7, 1 over 1 point, right, that is my fraction, 1.7. Now we usually don't read something as 1 divided by a decimal, so let's go ahead and rewrite this. 1.7 would be 1 7/10. This would be 10 times 1. We're trying to switch this to an improper fraction. 10 times 1 is 10 plus 7 is 17 over 10, and when you divide by a fraction you multiply by the reciprocal. So that's my convergent value. Now this one is actually alternating, because if I have my exponent here is odd, this is going to be a negative value. If my exponent is even, this will be a positive value. So I'm adding these positive and negative numbers, and you'd think, well, they'd cancel each other out, but they don't, because these are exponents that are different values. And it turns out they do converge, and they converge to the value of 10 over 17. So that's a really interesting one as well. Sometimes you'll be given a series of some sort. It might not necessarily look geometric, but you can rewrite it so it is geometric. Let's go ahead and look at a couple of these. Let's look at one where we go from m equal 2. Please note that we're starting at 2 here, not at 0, to infinity of 6 over 5 to the m. Now this doesn't fit our standard form. This doesn't look like a geometric series, but I can rewrite this. The 6 is not being raised to a power, so I can pull it out front. It's the 5 that's being raised to the power. So this would be 1/5 quantity to the m. Now this looks like a geometric series. Now if I want to determine whether this converges or diverges, I can look at the value of r. So r is equal to 1/5. The absolute value of 1/5 is going to be equal to just 1/5, which is definitely less than 1, so I want a less than sign here. Therefore this converges. Okay, so now let's go ahead and talk about what it converges to. Now this one's pretty exciting. It doesn't converge to a over 1 minus r because I'm not starting at 0 here. So what I need to do is I need to rewrite this into two pieces. So let's go ahead and look at m equal 2 to infinity of 6 times 1/5 quantity to the m. That's going to be the same as m equals 0 to the infinity, which is now that nice geometric series that I can use a over 1 minus r on, 6 over 1/5 quantity to the m. Then I have to subtract out 0 and 1 because I started this off at 2. So I need to go ahead and subtract out the sum m equals 0 to 1, two terms, 6 times 1/5 to the m. So this first is a geometric series, definitely a geometric series. This converges to a over 1 minus r. This piece is not a geometric series, this is a geometric sum because this is not going toward infinity. And what we want to think about here is this is two terms. So this converges to a 1 minus r to the n over 1 minus r. So let's go ahead and plug everything in. A is 6. 1 minus r is a fifth. Okay, now for my next one, a is still sixth. 6, 1 minus r to the second, because I have two terms here, over 1 minus r. But we know r is a fifth, so I better put that in there. And it's the 1 and the 5 that are both squared. So I need to make sure I have parentheses there. And so now all that's left is really to crunch through this. So I'll have 6 over. This would be 5 fifths minus 1 fifth is 4 fifths. Okay, minus the 6 out front as well. 1 minus 1/25 over 5 fifths minus 1 fifth is 4 fifths. And again, don't skip any steps here. You get to know a lot about these geometric series and some of these relationships when you're plugging and chugging through these. If you just shove this into a calculator, you're really not learning much. 6 divided by 4 fifths is the same as 6 times 5 fourths minus 6. And then with this 6, you divide by a fraction, you multiply by the reciprocal. So that's the reciprocal that I popped up here. And then 25 minus 1 over 25 is what we have here. So I could reduce this. So this is 15 halves minus, and then 3 times 5 is 15 halves again, but this 15 halves is multiplied by 25 minus 1 is 24 over 25. And of course that reduces as well. 2 goes into 24 12 times, and these are both divisible by 5. So let's see what we have here. We have 15 over 2 minus 12 times 3 is 36 over 5. Okay, finding that common denominator, I'll have 15 times 5 minus 36 times 2 all over 10. Continuing to simplify, it would be 50 plus 25 is 75 minus 72 over 10, which is 3 over 10. So again, don't skip any steps. This is where credit is given as all of this detail work. So 3 over 10 is what this converges to. Now be careful, anytime you don't start your series at 0, you need to make sure that you're compensating for that. Because if you don't compensate for that, your estimate will be high. It'll be too high. So again, a lot of times you have to rewrite these before you can actually get it into a geometric series form. This next one, I'm not going to go through the process of finding whether this converges or diverges. I just want to practice rewriting this. So rewriting this one, if you look at this, I have this -4 and I have the j, but I know that when I write this, it can just be j as my indice. I can't have that -4 up there. So I need to flip this. This would be 1 over 2 to the 4th. Let me make sure that looks like an exponent, with that 1 out front. So again, this is an implied 1 here, and so rewriting, this is j equal 1 to infinity of 1 times 2 to the 4th is 16 to the j. So now this is in a nice geometric series form. I need to note that I'm not starting my indice at 0, so I'd have to compensate with that if I decide that this converges. But this is how you'd work through or start working through this problem. So this was just a setup. The work that needs to continue here is to determine whether it converges or diverges. Let's look at another example. Oh, that one's pretty similar to the one we just did, so let's find a different one. Sometimes you'll see them written with a coefficient out front, and so we'll look at this one in terms of just rewriting. Sometimes they'll have this coefficient out front, and let's say this one will go from k equals 0 to infinity. Let's do an alternating. A -1 to a power will end up alternating, but depending on whether my exponent is even or odd. And then in the denominator I have 3 pi quantity to the k. So it's easy to forget this 7, so I like to pull it inside, and that's our value for a. So this would be 7, and then I could rewrite all of this with the k as -1 over 3 pi quantity to the k, and then you can work forward from there. But again, always look out front. Sometimes they sneak a constant out front, and it's easy to forget it, and it will kind of throw the whole problem off if you don't have it in there. One of the fun things that you can do with the geometric series and looking at the sum of a geometric series is you can take a repeating fraction and find out, or a repeating decimal, and find out what the fractional form is. So for example, and we know this one, so I'm going to start with one that we know, 0.3 repeating. We know 0.3 repeating's fractional form is 1/3. But we can use geometric series to establish that as well. And then of course I know that we know it's a third, but I'm going to establish it using geometric series and showing you how the process works, and then you can apply it to other problems as well, and these are fun. So let's go ahead and look at this repeating decimal, this 0.333. And of course this goes on forever. So this is equal to 0.3 plus 0.03 plus 0.003. You kind of get the idea here. And this pattern continues on. Well, 0.3 is 3/10. 0.03 is 3 over 100, 3 over 1,000, 3 over 10,000, etc. Now, if you look at this, the constant that's for each of these is definitely a 3. So I want to figure out how I could rewrite this. So if I want to put this in geometric series form, it looks like there's a 3, and then I have some power here. And it looks like to me that power is a 10th. 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000. So I kind of think it looks something like this. And then k equal 0 to infinity. So let's check it out and see if I'm right. So if I put k equals 0 in, I get 3 times 1/10 to the 0, and I'm already in trouble. 1/10 to the 0 is 1. 1 times 3 is 3, so this doesn't work. Okay, so I need to try something different. I think what I'd like to try, I got a 3 here, and I wanted a 0.3, so let's change this to a 0.3 and see how that goes. So let's go ahead and try it out. So 3 times 1/10 to the 0 plus, or sorry, 0.3 times 1/10 to the 1, 0.3 times 1/10 quantity squared. So let's see what this looks like. 1/10 to the 0. Okay, 1/10 to the 0 is 1. 1 times 0.3 is 0.3. 0.3 times 1/10 would be 0.3 divided by 10 is 0.03. 0.3 divided by 100 would be 0.003. So this looks like it's good. So I think that k equals 0 to infinity. 0.3 is my value for a. It's also my first value here. 1/10 to the k. And then what I do is I take this and I say, does this converge or diverge? Well, r is 1/10, and the absolute value of 1/10 is definitely less than 1, so therefore this converges. And specifically, it converges to a over 1 minus r. A in this case is 0.3. R is 1/10. So 10/10 minus 1/10 is 9/10. When you divide by a fraction, you multiply by the reciprocal. It's 10 over 9 though. 0.3 times 10 is 3 over 9, or a third. And again, we already knew it was a third, but I wanted to show you the process, kind of on a problem where we knew what the outcome would be, so we can focus more on the process instead of the outcome. So that's how you would work with these. Now everyone's a little bit different. Sometimes you'll have 2 or 3 digits repeating. Sometimes you'll have a constant out front. You'll have an integer value out front, and then with your decimals following. So those will be a little bit different as well. So these are a bit of a challenge, but they're, like I said, they are fun problems, and it's important to be able to work through these and not skip any steps. And again, coming up with a third isn't the difficult part. The interesting part of this is taking the 0.3 repeating, going through this process, not just popping in an answer, but going through this process of trial and error and finding the series that works. And then once you find the series that works, to go through to show that it converges and then show what it converges to. So good luck with these problems. They're fun. Make sure that you work through these step by step, because that's what I'll be grading on. As usual, if you have questions, please feel free to shoot me a text. You can also give me an online office hour time that would work for you. And of course, you also have the Pearson Connect to a tutor. Good luck and enjoy these problems.